Good morning to everybody. My name is Giuseppe Sarita. I'm Principal Scientist at Waters Corporation. Today I'm going to talk to you about a poster titled Collision Cross-Section of Common Cellular Metabolites to Support Metabolomics Applications. This work has been done in collaboration with the University of Iceland and Duke University in North Carolina. Metabolomics aims to screen small molecule metabolites present in biological samples. The development of a very reproducible analytical workflow and the identification of small molecule metabolites represent a major analytical challenge for metabolomics. In this work, we investigate the use of ion mobility in support of more traditional UPLC-MS methodology for metabolomics applications. Ion mobility allows us to calculate collision cross-section, which is a measure of the molecular shape of the analytes of interest. In this work, we measure the reproducibility of collision cross-section calculation and the use of this information in a common metabolomics workflow. The instruments that were used for this work were Synapti instruments, which were based in 3 different laboratories in Iceland, in Manchester, UK, and North Carolina. Also, we used the UPLC based hydrophilic interaction chromatography with the column 150 millimeter long and BH-amide 1.7 micron particle size. Also, we used either commercially available standard or real biological samples for these applications. The first step involved the calculation of collision cross-sections of metabolites. For this, we used a calibrator of polyalanine in measuring both positive and negative ionization mode. The first panel in the figure 1 shows the calculation of collision cross-section of drift times of polyalanine, which was infused in our Synapti instrument. The value of drift time of polyalanine were used together with their known collision cross-section to build calibration curves, which were used to calculate, to interpolate value drift time of unknown molecules, which together with their retention time and exact mass went to build the first ever database containing common cellular metabolites and not only exact mass and retention time but also collision cross-sections. The use of a calibration curve allowed to use different settings for ion mobility for collision cross-section calculation. In this example, we show that we could use different wave velocity and wave heights to obtain 2 different drift time for the same metabolites, which, however, after calibration curve, led to very similar collision cross-section values. Again, the use of calibration with polyalanine allowed us to use different instruments based in different laboratories. As you can see in the panel interlab reproducibility, shows that 73% of the calculated collision cross-section had a lower than 2% standard deviation, while other 15% had a standard deviation between 2 and 3%, suggesting indicating a very high reproducibility in the measurement of collision cross-section. We measure collision cross-section not only using standards, but also using real biological samples such as urine, plasma, extracts from platelets, and red blood cells. These collision cross-section were measured and compared with the values of retention times using a UPLC helic chromatography. As you can see in this panel, we obtained collision cross-section values which were highly reproducible, with 97% of the value having lower than 2% standard deviation. These values were compared with retention times, where 80% of retention times had lower than 2% standard deviation, indicating that collision cross-section measurements were more reproducible than retention times, and they could be used in support to retention time coordinates for obtaining more specificity or identification. The analysis was conducted using Transomics Informatics version 2.0, which allowed a database search based on exact mass, retention times, and collision cross-sections. In addition to collision cross-section, ion mobility was used to increase the specificity of identification in HDMS2D mode. As you can see in the figure, metabolite identification using HDMS2D. Without ion mobility, we have a much more complicated spectrum for both precursor ion top panel and fragment ions in the lower panel. However, when ion mobility was turned on, we will have a much better, much cleaner spectrum for precursor ion and fragments, which allow a better identification, more specificity identification. In conclusion, we calculated collision cross-section for over 120 common polar metabolites. We showed the highly reproducibility of this measurement using different instruments in different laboratories. And we showed the power of using collision cross-section in combination with retention time and exact mass, which allowed us to build databases which can be used to increase the specificity of identification and improve data interpretation. Thank you for your attention.